we could actually solve this, and we got something crazy. We got this equation, I'll just write it down, that the expectation of psi you might remember this. That's what we actually, by taking derivatives here, you look at your notes, this is what we got. Where the norm was the ergodic norm. So you basically, so as long as you can justify taking the derivative inside the expectation, you get this expression, which is the least squares solution. I mean, it's basically any least squares problem, that's the answer. This is an inner product, by the way. The problem was that h is the thing we don't know, so you have to write this in a different form. So what we showed was that this is equal to the expectation of c of x times what I called, sort of psi beta. And what psi beta was taking this and passing it through a low-pass filter. So if you'd like, put an n there, and n there. Okay. So I take this, I take psi stationary, pass it through a low-pass filter, and I get this thing here. And that's the one thing that's brilliant about TD learning, is that you take a least squares problem, it's a standard solution for least squares, but you take something that's unknown, something in the future, and you make it into something in the past. Because it's a causal filter, you take past observations of psi to generate it. And so you get a recursive output. And so given this, here's what's called LSTD learning. So let's write this as m times theta star equals b. We want to estimate b and m. Well, Monte Carlo, just simulate. Okay, so to get to estimate this matrix, that's stochastic approximation, but all it is Monte Carlo. Remember we saw that? We saw that this equation was exactly just averaging psi set transpose. Okay, so we got estimates of this matrix. And we want to estimate this. Well, I just told you, you pass psi through a low-pass filter. So that's what I meant by that block over there. And then finally, we're trying to estimate the expectation of this low-pass filtered psi term in C. We'll multiply them together an average. QED. I guess with the additional step, we have to define theta. So you solve this equation to get theta. Okay. And so basically, I mean, and you know, I guess if some of you care, you know, there's something called the matrix inversion lemma, so you can update the inverse recursively. I won't bother you with that. And basically, that's it. So that's least squares temporal difference learning, and it works beautifully. If you compare, if you look at the chapter in my book on TD learning and least squares temporal difference learning, I give comparisons, and where TD learning just doesn't work, the variance is so large. It's just looks like a charm. So, of course, it's more complex because of matrices, but that's that. Nailed it. So, you know, I mean, can you imagine all the marketing around this when it's such a simple thing? I mean, it's ridiculous, you know. It's ridiculous. It's just a simple, elegant idea, and it's just, you know, it's way over marketed. It's just a very, one beautiful step there, you know. I love it. Absolutely. That's it. Okay? So one person here had a brilliant question. Why are we bothering? So I claimed that we were trying to find this because we were going to do policy improvement. That's one reason. So can I erase this? I'm not going to need it again. This was a question that was asked to me yesterday. So what? We've got a really good approximation maybe to the value function. What do you do with it? Now it may be that we do care. We're trying to forecast our income over the next time horizon, and that's what you do use it for. But I claim that you could use it for policy improvement. This is what I claimed before, that given an approximation to the value function, oh, there's a beta missing. This is how you would do policy improvement for a discounted cost. But there's two problems with this. First of all, this is approximate dynamic programming. It's not reinforcement learning. You require knowledge of PU. Given these conventions, it's approximate dynamic programming and not reinforcement learning, which is too bad. And secondly, it requires multiplication. Now, I mean, you know, I've been saying we're doing all the analysis in countable state spaces. Everything's countable state spaces. In reality, you can almost always have a general state space. TU is going to be some mixture of Gaussian kernels, maybe if you're lucky, and H is going to be a bunch of polynomials. Maybe then you'll get a closed form solution. Most of the time, this integration step itself is a nightmare, you know, absolute nightmare. And for a large state space with you know, some complicated statistics. So this is, having to do this to compute your policy for every x is a nightmare. You know, what about the beauty of Q learning, where you get like Q function and there's nothing more to do? So there's a solution to this. And I couldn't remember what it meant, so I looked it up again. It's state reward action. Blah, 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 blah. It's hilarious. state action rewards state action. Is that really true? No, that's a mistake. That's a typo. That's a typo. No, I don't know. What is it? So I think it should be called QQQQQ for high quality. I mean, it's just absurd. So this paper, it appeared in a technical note in Cambridge in 1994, and it never saw the light of day. The paper was never published. And I'll explain why. So again, this was a clever idea. I'm not discounting it, but they didn't realize that it had already been done in a sense. That there was there's a really clever trick. I mean, this is a real issue. We don't want to know PU, we don't want to integrate, and so you need an alternative, and they found it. It just turned out there's nothing to do. If they wrote a paper, it would be half a page long. I'll do it, so in the next half hour I'll write down a half page. So references are in the email I sent, well, in that book chapter that I sent. So you've got the references there. And again, there's no disrespect to them. It's just this is a technical report, and there was a connection they didn't see. Okay? So here's the fun. Here's the idea. This was in 1994. That's when the technical report came out. So here's the idea filtered through, after 20 years of thought. So it's not their idea, but this is the way we should think about it. So remember that if I take U of t to be phi of x of t, z of t. And so remember, I'm looking at randomized stationary policies because I need to explore. So this is what I'm going to be doing throughout. This is when I start with TD learning, I said I have a policy like this, so we've just got a fixed Markov chain. So x of t is a Markov chain. Okay, again, that was the whole justification for the TD learning. I said once we have a policy like this, we have a fixed Markov chain, we can now estimate value functions. But also the pair is a Markov chain. Because, well, it is. U of t is a function of x and t of noise. Well, that's a function of a previous x of t and u in noise. I mean, you could go and check it. The pair process is Markov. Exercise. All right? And the idea then is let's play around with that. So what I first have to do is I have to go back to the beginning and justify what I was doing before, the TD learning. Let's go back and think about what I had done before. So what I'm going to do is I'm going to denote C bar of x equals the expectation of the cost with this policy in place. So this was behind the scenes before. I've already done this. So the h of x that I defined before So remember before I said, well, u of t is just fixed by a policy like this, so let's suppress the dependency on u. I'm not going to suppress it anymore all the time. I will for a moment. So this was the justification for going through TD learning and LSTD. What I want to do is, instead of using this, I want to go back to the dependency on two variables and use the fact that the pair process is Markov. But for that, I don't want to condition on x equals x. I want to condition on the entire initial condition of the bivariate Markov chain. So for that, we need some new notation. Let's call it capital H. Okay. So now I'm viewing the pair process as Markov, and H is just exactly analogous to this. And the only difference is I'm conditioning on the full initial condition of Markov, the bivariate Markov chain. Now let's play around with this, and we're going to find that this solves our problem. So let's see. There's a few steps here. So first of all, I'm conditioning here. I can take out the first term. It's just given. And if I want to, I can, well, let me do a few things at once. I'm going to take my time. If I unravel in this way, this is how you derive the dynamic program equation. You know, this is precisely the discounted cost dynamic program equation, that the value function is equal to the initial cost plus beta times the cost to go. Okay. So it's nothing new there. That's exactly the dynamic program equation I wrote down before. Nothing new.
So this is kind of the discounted total cost average cost equation.
Well, it's what we used before. Remember I said before that I said that h of x plus c of x. I'll put a bar there now, with plus beta pu h of x.
Yeah. So
this is exactly the same as this for the bivariate chain.
And for this equality, is it the optimality condition for the total cost?
Optimality. There's no minimum here. So this is just the dynamic program equation for fixed policy. Yeah. So this function here satisfies this. There's a proof. So, yeah, that's really the proof. That basically that this total cost is the initial cost, and then by pulling out a beta here, I see that this is exactly the same as what I started with. So just take a look at this. I'm summing from time 1 to infinity of the discounted reward. So there's no optimality because it's a fixed policy. Okay. I mean, so anyway, so we have that, but we have more too, because after all, u1 is a randomized function of x1 and all that. Here I can replace this by c bar as well. I don't want to rush this too much. So you've got this all embedded in your brains. And H is just this discounted cost here. Keep that in your brains. Every one of these terms can be replaced by a C bar. I'm just going to rewrite this whole thing again. For the exact same reasons. That U is just a randomized function of X. It's just exactly, you believed me before, why not believe me now? The expectation of this is the same as that. Okay, it was how I define C bar is the expectation of that. And what you get from that is that this is equal to C of XU plus beta times the expectation of H of X. 1. Really what I'm saying is that this conditional expectation and this conditional expectation are the same. Because all this is the cost to go starting at time t equals 1. And starting time t equals 1 was starting at x of 1. Okay. All right, so here I am. I've gone to step time 1, and I want to look at my remaining cost to go. The t minus 1 is useful because at where I start, I want beta, beta to the 0. I get it. So this is just the expectation of this, starting at x1 is the cost to go from there. So there's two representations here, but the first thing is that is a definition that H is the discounted value function for the bivariate process, and it satisfies the dp equation. But also, it looks like this looks just like the Q function. There you have it. So they didn't, the authors of this paper, of Sarsa, didn't recognize that that's what they were doing. They didn't recognize that they were starting with the bivariate process and then coming up with this equation. They came up with Sarsa was a way to try to estimate this stuff. But the point is there's nothing new to do now. If I'm interested in estimating this quantity for policy improvement, if I have an estimate of this quantity, that's what we minimize over U for policy improvement. All I have to do is run standard LSTD or whatever for capital H. I forget about the univariate Markov chain X. I look at the bivariate chain, get an estimate of capital H. Well, capital H is precisely the thing I wanted for policy improvement. So there's a few concepts there at once. this has got you all stopped cold. So I've got to do something about that. I guess what's confusing some of you is I'm slipping in extra conditioning. You know, is that I'm, and I'll only say given x1. So here I've got this sum here, and I'm conditioning on two things, x2 and mu. Let's condition on one extra bit of information. Okay. And given x1 equals x1, that's enough information to predict the future. This becomes irrelevant. Okay, so that's a property of controlled Markov chains. Okay, that once I know x1, I don't need to know x0 and u0 for predicting the future. Okay, and then I can go through and use the time homogeneity. I can shift t by 1, starting from 0 to infinity, and instead look at x0 equals x1. These are the same because I can always shift time. This is just think about it physically. I'm starting at x1, and I'm looking at time going from 1 to infinity. Well, let's redefine 1 to be 0. That's what I've done here. I'm just redefine my time indices, and that's exactly equal to h of x1. So that's all I've done here. Is I've actually stuck in a conditioning with respect to x1 as well, and then it's moving there. Yep.
Do you also need to know u1?
Well, you're right. I mean, if I was just talking about, if I was just using the fact that, wait, u1. No, I mean, I do. I'm just using the fact that this is a controlled Markov chain. So, because u1 is only useful for knowing future instances. All right. So there are a few steps really in going here, but those are the steps. All right. And so there you have it. Sarsa is that if you can estimate the value function for the bivariate chain, then you've got this sort of something like a Q function. Generalized for the new century, now that this is all much better understood. Sarsa just means estimate h using any technique you like. Okay. In the original algorithm, they used TD with. Or TD, or what's called TD lambda, which I refuse to talk about. But anyway, this is just a value function. XU is just a Markov chain now in this interpretation. That's sort of step one. 2 is interpret. There's nothing more to Sarsa. Is that interpret now? Once I've estimated h, I can use this interpretation to generate, to obtain an algorithm, TD or LSTD algorithms, right? Given any value function like this, I can use the algorithms we developed. Okay? But now I'm going to use this interpretation for policy improvement. So I ran out of room. There's no way to fit this in. So I don't want, that's too small. If I believe that this is an approximation of this, the argument of this over U is exactly policy improvement. And that's it. You know? So all this letter is for that simple idea.
That's it, but you have to repeat.
And then you have to repeat.
So every time I want to improve the policy, I have to redo TD learning, which is already not bad.
Well, no, TD learning, I mean, what's beautiful about LSTD, well, both of these, if you have a linear parameterization, it's a convex optimization problem, and you're assured to get to a global minimum. And yeah, I mean, depending on the problem, the variance can be higher or not. Yeah. The problem with Q-learning is nobody's come up with a convex algorithm, you know, for reinforcement. That's been the gap. Like I mentioned, the two cases where they have is optimal stopping and the deterministic algorithm I mentioned. But besides that, it's the frontier. So this is really the only thing you have. And luckily, policy iteration converges really fast in terms of steps. So for real policy iteration, when you can implement it, it's like, you know, I mean, often 5 iterations is enough. So it's not that bad in a sense. I mean, of course, you know, I have to admit, I haven't looked at really high-dimensional problems. I'm not sure anybody has. You know, I'm sure there are problems that are really hard. I've been lucky. You know.
I don't want you to provide a proof of this, but is there a proof that you still get policy iteration to improve?
No way, it doesn't improve.
No, okay.
It doesn't improve. Because the thing is, here's the biggest, here's the nightmare about it. The fact that I have to iterate this is not a problem. What are the issues? So let me come back to that question about convergence, about improvement and all that. So the first issue is, what about a basis? You know, now I realize I'm forgetting to say this. I hope it's all internalized. That I've been developing these really naive models for relatively complex systems, like that speed scaling model, the fluid model, gave a value function approximation for Curie models, and that's true in so many examples. You can come up with really naive models, and they give you a basis in approximations of a value function that you can feed into these algorithms. Okay, so you know we already know ways of getting approximations for H. I mean, I've been sticking to the average cost case, but the discounted case is similar. So if we have first of all, assume we have a linear parameterization. Like those are fluid value functions, mean field limit model approximations, something you got from Taylor series, something you got from diffusion approximations, I don't know, whatever your favorite approximation techniques. You get a bunch of approximations, just throw them all together. Secondly, I'm going to need to know something about the system. So some approximation to P. So something that's simpler to compute, work with, you know. So this, I said integration is hard. I'll choose this so integration is easy. I'll choose it so I get a decentralized control algorithm. I'll choose it, you know, so it's convenient for me, you know. And then I'm going to just go through and define an affine parameterization. I get some of this out. That's supposed to be an uppercase psi, and it's just P acting on little psi. So I'm expanding this out just to emphasize the fact that I still have to perform an integration, but only with these D functions, you know. And I'll choose them so this is something I'll choose P hat and psi so it's something I can actually compute in closed form or approximate. And maybe put it in. Maybe it's only an approximation. You know, maybe I can't compute it. I'll just approximate. You know, but that's so conceptually coming with a basis is not as no harder than it is originally.
Did you drop the theta in the second to the bottom line?
Oh yeah, thank you. There we go. So anyway, so choosing a basis, I think there's a clear path to that. What about convergence?
Excuse me, what does this kind of integrals usually mean when D is as a parameter?
I mean, an example. Something like that. If I wanted to find PU H of X, that's an integral. That's equal to an integral of H of X minus U plus A. Maybe there's a density piece of A of A dA. Now, of course, we'll assume A has integer values with the sum, no problem. But maybe that makes things harder. Maybe A is more naturally Gaussian, and maybe A lives in dimension 5,000. This could be really ugly. And the thing just bounces around. There's still a lot of work to do in theory here, just to get something elegant. so maybe you could just forget, to avoid all this horrendous, scary, small exploration. Maybe there's some way of doing it either with a deterministic policy, and for that, see this paper I sent you. And this is a beautiful mathematics. I don't know if it's a practical algorithm, but this is another approach you can. It basically it uses something called accordance sampling to try to explore and get rid of the exploration. I'm not going to get into that. That's really technical. Okay, so I'm supposed to stop, aren't I? So I stopped 1 minute ago. So I think that's all I'm going to say. I mean, I've given you guys all what you need for TD learning, Q learning, SARSA, and I've given you hints on the theory. So the remaining lectures, I'm going to sort of develop the theory. And we saw that there was TD learning, which I sort of said is really can be high variance. Q learning is much better. So there's theory to justify stochastic approximation. I mean, TD learning. It's called stochastic approximation, and it has high variance. There's a fix. It's exactly the same fix as Q learning. And it turns out that what it is it's the steepest descent, and there's Newton-Raphson. And it turns out that in the stochastic realm, there's steepest descent, which is stochastic approximation, and there's a Newton-Raphson algorithm as well. And so you really need these tools. I mean, just having these 3 algorithms isn't enough. So I encourage you to attend the next lectures. I know you have no incentive now, but anyway, that's the remaining lectures will be just talking broad strokes about the general theory of these algorithms.